So firstly, I'd like to thank the organisers for having invited me to fill in this slot. Always feels like something of an honour to be able to contribute to what's been so far. Really very good, great conference. Anyway, so I'm going to talk about plateau problem for general curvature functions. So this is the content of these two papers that I have on the archive. Basically, when they asked me to give this talk, I was thinking what would be the most appropriate thing. And it seemed to me that the work that I completed the last time I was here in IMPA would be most appropriate for a talk in IMPA. So, apologies to anybody who's seen stuff like this from me before. So before I get started, it's just worth mentioning a couple of the names who work in this field who are not going to be mentioned in the talk. The thing is, I mean, there's a lot of people studying non-linear plateau type problems, and to give an exhaustive list would be practically impossible. But the most significant names for my own work are, of course, my PhD advisor, Francois Laberie, a chap called Ivoshkina, who did stuff very similar to what I do. There's Antonio Martinez from Granada and friends, and of course Harold, whom we all know. So these are, but the list goes on and on and on and on. There's lots of names in this particular field. So anyway, start by discussing the framework, exactly what it is I'm looking at. I'm looking at immersed hypersurfaces in Riemannian manifolds. So by hypersurface, I mean that they're of codimension 1. So setup is the following. You want to keep this picture in your head. So you let M be any n plus 1 dimensional complete Riemannian manifold. You let N be a compact n-dimensional differentiable manifold with boundary. And you consider immersions from N into M. So what that means is I is a smooth mapping whose derivative is always injective. So the main difference between, the only real difference between an immersion and an embedding is that you can have self-intersections of that. So immersions are more or less embeddings. So once you introduce the concept of immersion, the first thing you want to do is you want to define the canonical objects that you want to look at. So the canonical objects for immersions are, firstly, given that we're in a Riemannian setting, the outward pointing unit normal vector field. We're assuming everything's oriented here, so this is a well-defined object. So of course it just looks like this. And from the outward pointing unit normal vector field, then you define the really interesting thing, which is a shape operator, which we call A here. Some people call it the Weingarten operator. And this is merely the derivative of the unit normal vector field. It defines an endomorphism of the tangent bundle of n and assigns a vector x to the derivative of the normal vector in the direction of x. And you can show, it's trivial, that that is also a tangent vector to n. Now, the point is, from a Riemannian setting, in Riemannian geometry, essentially the only thing that really matters is curvature. Which says then that for immersions, in a way, the only thing that really matters is the shape operator, because the whole point of the shape operator is the shape operator contains all the curvature information of the hypersurface, which is to say that the curvature of the hypersurface can be deduced from the curvature of the ambient space and the shape operator from a very well-known formula, very simple, very well-known formula. So, now we have the concept of immersion. We want to introduce scalar notions of curvature for immersed hypersurfaces. So, the idea is we want to look at notions of curvature like extrinsic curvature, some people call Gaussian curvature, like mean curvature, but we want to generalize this. Now, for the sake of this talk, I'm just going to restrict attention to notions of curvature which are only defined for locally strictly convex immersed hypersurfaces. We say that an immersed hypersurface is locally strictly convex if and only if its shape operator is always positive definite. So, we consider the convex, so in particular, if the shape operator is a positive definite, its principal curvatures will always lie in the convex cone in Rn. So we look at this convex cone, let's call it, convex cone, the positive cone in Rn. So we look at this cone of positive vectors, and we look at functions defined in this cone. We take a smooth function k, and we say that k is a convex curvature. K is a positive smooth function. We say it's a convex curvature function if and only if it satisfies, 6 conditions. First 4 conditions are very natural geometric conditions. The first one is that the function has to be invariant under permutations of the coordinates. And that's obvious because curvature is defined in terms of the principal curvatures. The principal curvatures are an unordered vector. So if you want this thing to give you a well-defined curvature, it has to be independent of the order in which you place the elements. Next thing you'd want from a geometric perspective is homogeneity. For a very simple reason that if you have a hypersurface, say sigma, in Rn plus 1, and if you take a homothetic rescaling of 2 times, then what you're going to do is you're going to divide the shape operator by half. And by dividing the shape operator by half, you also want to divide the curvature by half. And that's where the homogeneity condition comes in. Next condition, third condition is not really necessary, but it's nice to have. Call it normalness or something. You want k of 1, 1, 1, 1, 1 to be equal to 1. This is because you want the curvature of the unit sphere in Euclidean space to be equal to 1. Finally, you have this condition of compatibility, and it's a compatibility condition that really gives the convex part of this definition, is that you want this function to extend to a continuous function which vanishes along the boundary. And this condition is very important for compactness results, because what that means is, suppose you have a sequence, sigma n, of locally strictly convex immersed hypersurfaces of curvature equal to kn. And you suppose that these sigma n converge towards a limit, sigma 0. And suppose that their curvatures also can converge towards the limit k0. Then what this compatibility condition tells you is that if k0 is greater than 0, then sigma 0 is locally strictly convex. So what that means is you can just read off from the curvature whether the limit is inside the interior of the set of locally strictly convex surfaces, hypersurfaces or not. That's very practical. Next conditions, which are important, are the utterly necessary conditions from the analytic perspective. First is ellipticity. You can't really do much without it. And in this context, the condition that you require is that all the partial derivatives of this function k are always positive. And what that condition is equivalent to is it's equivalent to saying that this is basically when you calculate the Jacobi operator associated to the curvature that this function defines, you'll find that the exact condition required to make sure that the Jacobi operator is always an elliptic operator is that one. Finally, you have this technical condition which arises from the theory of nonlinear partial differential equations, is you require k to be a concave function. And there's really not much you can do unless k is a concave function. So, consider examples. So, once you've defined this curvature function, you can then define scalar notions of curvature for hypersurfaces by just saying that if you have an immersion I, you define the curvature of the immersion to be equal to k of the principal curvatures of the hypersurface, which is to say the eigenvalues of the shape operator. So, typical case would be if you let k of lambda 1, lambda n, just to be equal to the product raised to an appropriate power, 1 over n, then you can show that that satisfies all the axioms, and what you recover is extrinsic curvature. But there are lots of other examples. One that I'm quite fond of myself is when you divide k by h. Then you obtain another notion of curvature which also satisfies all these axioms, where h is here the mean curvature. And you can go on like that, just inventing as many notions of curvature as you like. You can take convex sums and convex products and stuff like that. You can just, they're huge families. So you've established the concept of immersed hypersurface. you've established the concept of scalar notions of curvature. Once you establish these two concepts, the natural question to ask is the plateau problem. Now, in the context of locally strictly convex immersed hypersurfaces, the natural plateau problem requires an outer barrier, this one. And so you ask the plateau problem with barrier, which is stated as follows. You consider I hat as a locally strictly convex immersion from n into m. And you ask for I hat to have the barrier property, which is to say that there exists, for k, you choose k greater than 0, and you suppose that the curvature of I hat is everywhere greater than or equal to k. So this is I hat here. Then, given such an I hat, which is an outer barrier for the problem we want to solve, the question then is, can we push that I hat inwards to get something of constant curvature equal to k? In other words, does there exist an immersion I from n into m, which coincides with I along the boundary, and whose curvature is equal to k? In fact, you can do a bit better. You can say that I is in fact isotopic to I hat, but I don't want to get into that. So, there's a lot of work done in this field. My favorite result is this result by Guan and Spruck, Trudinger and Wang, published simultaneously. It's exactly the same result, published simultaneously by these chaps. And it goes like this. You let M be n plus one dimensional Euclidean space. You let K be the extrinsic curvature. So that's what you obtain when you take the product of the principal curvatures or the determinant of the shape operator. Then for any locally strictly convex I hat whose curvature is everywhere greater than K, there exists a smooth locally strictly convex I with the same boundary whose curvature is equal to K. Now, just a word of note, this paper in particular is a masterpiece of clear writing. It's beautiful, and I'd recommend it to anybody. It is one of the most beautiful papers I've ever read. Now, lots of other results in lots of other improvements. In 2004, Guan and Spruck improved on this, and you can deal with curvatures of the form k0 to the alpha, k1 to the 1 minus alpha, where k0 is equal to an extrinsic curvature, and alpha is strictly greater than 0. Alpha is somewhere between 0 and 1. In particular, that doesn't include cases like this one. Then Sheng, Urbis and Wang, shortly afterwards, addressed a specific case for k's of the form sigma n divided by sigma k, where sigma k is a k-symmetric function. So that does in particular include this one, but not various other ones. So, I've always been interested in these problems in, well, firstly, hyperbolic space and Hadamard manifolds. My own particular reason comes from the work I started doing for my PhD supervisor several years ago, where he was looking at Hadamard manifolds. So, when I saw Guan and Spruck and Trudinger and Wang's result, my natural inclination was to ask, how can you try and prove the same result in the general Hadamard manifold? Well, if you want to use Guan and Spruck and Trudinger and Wang's techniques, you encounter immediately big problems. Because these guys used, firstly, C01 compactness theorem for locally strictly convex immersions with given boundaries. So this is kind of the substrate compactness theorem for everything else. Then they use the Caffarelli-Cohn-Nirenberg-Spruck compactness theory for second order elliptic totally nonlinear partial differential equations boundary value problems, which was developed in the early 80s. And then, in order to move from local to global, they have a very nice application of the Perron method. Now, the problem here is steps 1 and 3 in particular, because these rely very heavily on the geometric structure of Rn plus 1. You need the entire space. You need to be able to ensure that through any point, normal to any point, there exists a totally geodesic hypersurface, which basically tells you that you're equal to a space form. So there's no obvious generalization. Nonetheless, introducing completely different techniques, in fact, you obtain a generalization which looks like this. So you let M now be any Hadamard manifold. well, you suppose that sectional curvature is bounded above by -1. You let k be a reasonable convex curvature function. Now, reasonable is related to behavior along the boundary, but it includes in particular all these cases and many more. Let k be a reasonable curvature function. Choose little k in 0, 1. Then, as before, we can show that for any locally strictly convex I hat, sending n into Rn plus 1, such that k hat is bigger than k, we can push it inwards and find a locally strictly convex immersion I, which coincides with I hat along the boundary and whose curvature is equal to k. Now, you can do various improvements in this in lots of different directions. When k is equal to when k is extrinsic curvature, the sectional curvature condition can be dropped. In fact, the sectional curvature condition can be dropped whenever you have something of that form. So the main ideas behind this proof, I really don't have time to go into detail, are you have to replace these things with some sort of equivalent or something that will do the job instead of them. So, the first one, the generalization of this thing almost looks the same as this thing, with a lot of work, and I would love to see a short proof of this. I couldn't find a short proof. The proof I got was very long and technical. But you obtain a C01 compactness result for locally strictly convex immersions near the boundary. That's the main difference with general manifolds. So you get your substrate compactness result, and you need to do the rest. Second step is you have to adapt Caffarelli-Cohen-Nierenberg-Spruch theory to the parametric setting. And this is quite non-trivial, and that's essentially the content of this paper. Sorry, I should say, so the C01 compactness result, that's really the essential content of the first paper. Adapting Caffarelli-Cohen-Nierenberg-Spruch theory is essentially the content of the second paper. Once you've done that, you just have to develop an appropriate degree theory, or continuity method if you like, depends what you want to call it, and you show existence. In fact, you can do even better than that. In some special cases, you can even prove uniqueness. For example, you can prove uniqueness if the curvature is equal to sigma n divided by sigma n minus 1, where the sigma k's are the symmetric functions, or sigma n divided by sigma n minus 2. That's another case where you can prove uniqueness. Or you can also prove uniqueness for special Lagrangian curvature. So some very special cases where you prove that the signature in the degree is always positive, and you thus obtain uniqueness. So, I'd like to conclude by just illustrating one of the key ideas in the proof. So it's one of the key ideas in the second paper is how to construct the barrier functions from geometric data. So basically, most of the compactness results in these papers are proven using barrier techniques. And the question then becomes how you construct barrier functions. And it turns out there's a rather neat system for constructing barrier functions which works as follows. You consider a foliation of your ambient space by convex hypersurfaces. So you let f then be the defining function of the foliation. So you let f be a function from the manifold into R whose norm is equal to 1. You imagine it's sort of a distance function, basically. Its norm is equal to 1, so level sets are convex, and the k curvature of its level sets are all bigger than k. So this is the foliation you've got. So you imagine it looks like that. Typical thing to have in your head, distance spheres to a point. Another thing you can think of is distance to a hypersurface of high curvature. And there are other examples we'll see in a second. Now, the interesting thing is the following, that if you have an immersion from n into m, which is also locally strictly convex, and whose curvature is constant and equal to k, then you have this relation for the Laplacian of the composition of f with I, which is to say the Laplacian of the restriction of f to I. Essentially, what this is saying is that modulo the first derivative, this function is subharmonic, which is quite a strong property. So the point is the Laplacian you use depends on the choice of curvature function. If k were the mean curvature, then this would be the normal Laplacian. But in general, you have to use a different Laplacian. Likewise, the norm here also depends on the curvature function. So, really, the heart of the matter is often then a question of finding the right barriers. So, in Hadamard manifolds, Busman functions, they were introduced in the first talk today, measure distance to points on the ideal boundary. So, the level sets of Busman functions are horospheres. We know that horospheres are convex. We know as well that if the sectional curvature of the ambient space is less than or equal to -1, then for all t, the curvature of the horosphere height t is always greater than or equal to 1, greater than or equal to any k less than 1. So Busman functions then yield pretty good examples of barrier functions. And that's why we have this condition here in this theorem. That's where the theorem is coming from. But it's not the only choice of barrier function that you can use. This particular foliation here is a singularity, but the singularity doesn't actually matter too much because it's in a way, it's going in the right direction. It's still convex or concave, so it doesn't matter. But you consider the distance, you now look at Rn plus 1. You suppose m is Rn plus 1. You consider distance to the origin in Rn plus 1. And for all t, you'd note sigma t equal to the level set at height t. So it's just a sphere of radius t. Then we know again that sigma t is convex for all t. And we know as well that for all t less than or equal to 1, the curvature of sigma t is greater than or equal to 1, which is going to be greater than or equal to any k less than 1. So this function d also provides a good barrier over the region where x is less than 1. So last slide. So in a way you can kind of see that the barrier condition that you need in a way is kind of natural by looking at this particular theorem, which is probably been proven. You can actually obtain it's a corollary of Guan and Sprook's result, including on Wang's result, but I'm just putting it here as an example of how you do things. If you let m be the if you let m then be n plus 1 dimensional Euclidean space, you let omega be any open subset of the unit sphere with a smooth boundary, and you let k be any reasonable curvature function, then for all k in the interval between 0 and 1, you can prove again that there exists a smooth, locally strictly convex immersion from omega into the ball, such that it coincides with, it's equal to the identity along the boundary of omega, and this curvature is constant and equal to k. So the picture you have is something like this. The ball is here, omega is a subset, and you have some immersion. Well, this isn't convex, but it should be convex. You have some immersion from omega into the interior of the ball, which is equal to the identity along the boundary. And moreover, you can do even better. You can show, just using uniqueness, that the immersion tends towards the identity map as k tends to 1. I think that's exactly 25 minutes.
Have some more.
Oh, well, it's finished. Okay. Yeah, so. Sorry? No, it's done. So, thank you very much for listening so politely.